Hi, welcome. So in one of my previous discussions, I talked about parity, especially in relation with neutrinos. So I said that neutrinos are left-handed while antineutrinos are right-handed. And I also said how this fact about our nature, that all neutrinos are left-handed and antineutrinos are right-handed, is basically a result of the violation of parity symmetry. Now I felt that that discussion was very basic. It was like an introduction, and I felt that there is a need to have a more complete discussion on the topic, and therefore I've made this particular video. So in this video I'm going to give you an idea about what parity is and what does it mean when we say conservation of parity or parity symmetry. And then I'm also going to briefly talk about the handedness of neutrinos and how it tells us about the violation of parity symmetry for weak interactions. And to do that, I'll talk about the very famous experiment which was performed by Chen-Xing Wu in 1956, which is also known as the Wu experiment, which for the very first time experimentally demonstrated the violation of parity symmetry for weak interactions. So let's get straight into the video. So the idea of a parity symmetry is essentially quite simple. It is a mathematical operation which simply flips the signs of the coordinate axis. So whenever a parity transformation is applied onto a given physical phenomena, then the physical quantities change in such a manner that the coordinate system itself flips its signs. So for example, whenever you study a physical phenomena, you always talk about the physical quantities with respect to some coordinate axis, right? If you have this kind of a coordinate axis x, y, z, the moment you do a parity transformation, you end up getting minus x, minus y, minus z, which simply means that these axes x, y, z gets inverted. And you go from a right-handed coordinate system to a left-handed system. Now what does that mean? So if you look at the one coordinate frame of reference on my right, it is a right-handed system in the sense that if I take my right hand and I use my three fingers, the index, middle and the thumb, so where the index finger is pointing towards the x-axis and the middle finger is pointing towards the y-axis, then my thumb will automatically point towards the z-axis. This is known as a right-handed coordinate system. However, the moment I do a parity transformation on this to end up getting this, then I cannot apply a similar sort of a representation to represent minus x, minus y, minus z, because this is not a right-handed coordinate system. In fact, this is a left-handed coordinate system. So in a way, the moment you do a parity transformation, you end up going from a right-handed coordinate system to a left-handed coordinate system. And therefore, whenever we talk about parity transformations, we usually talk about mirror images, in the sense that when you stand in front of a mirror, your right hand becomes your left and your left hand becomes your right. And in that sense, sometimes parity transformations can be visualized in terms of mirror images. I'll come back to that point just in a moment. Now, when we do this kind of a parity transformation, what happens is that certain physical quantities may undergo a change in its sign and some of the quantities may not. So for example, if you define the position vector of a particle which is moving through space, then the position vector is defined with respect to x, y and z, right? So since x, y and z experiences a flip in the sign under a parity transformation, so the position vector will also experience a flip in the sign. So r will become minus r. Similarly, linear momentum p will become minus p, acceleration a will become minus a, force F will become minus F. Some physical quantities, however, do not experience a change in its sign or direction. So for example, angular momentum. So angular momentum is nothing but the position vector cross product and the linear momentum. So minus r cross minus p is nothing but r cross p, which is L. So the direction of the angular momentum remains the same even under a parity transformation. Now in the same sense, when we talk about spin angular momentum of quantum particles, even the direction of spin angular momenta will not undergo a change in direction under a parity transformation. Now what I want to say here is that let's suppose that a particle is experiencing some sort of a trajectory due to the experience of some sort of a force. Now the mirror image of that trajectory, or the parity inverted trajectory, is nothing but the same particle undergoing a force minus F with respect to an inverted coordinate system. So in a sense, both the trajectory as well as the mirror image of the trajectory are equally likely, and they are a result of the Newton's second law. In a sense, the Newton's second law does not distinguish whether or not the particle is being studied with respect to the xyz frame of reference, or whether the particle is being studied with respect to minus x minus y minus z frame of reference. So in a sense, the physical law itself does not distinguish whether you are in a right-handed coordinate system or a left-handed coordinate system. So we can say that the physical law F is equal to ma is invariant with respect to this kind of a parity transformation. So not just the Newton's second law, even the law of gravitation or the Maxwell's equations themselves are all invariant under a parity transformation, in the sense that they will lead to evolution of physical events which cannot be used to distinguish whether or not you are in a left-handed universe or a right-handed universe. So in a sense, the physical laws are incapable of distinguishing whether the events are taking place in a right-handed universe or a left-handed universe. And even if you talk about quantum physics, let's suppose, in quantum physics, let's suppose you have a certain potential and you apply the Schrodinger's equation on that particular potential to obtain the probability distribution of where you can find the particle. And if you do the same with the mirror image of that potential, so v minus xt, and then you apply the Schrodinger's equation on that potential to obtain the probability distribution. So both these probability distributions are equally likely and will be nothing but the mirror images of each other. So both these probability distributions are equally likely and are a result of the Schrodinger's equation, which does not distinguish whether or not you are using this potential or that particular potential. One of them is not forbidden, both of them are equally likely. As you can see here in this kind of a example of a square well potential. So if you draw an axis vertically with respect to the square well potential, and you consider the right hand side to be with respect to plus x, and you consider the left hand side with respect to be minus x, then let's suppose for n is equal to 2, you end up getting this kind of a probability distribution where the right hand side is nothing but the mirror image of the left hand side, right? And both of them are equally likely and arise as a result of the Schrodinger's equation applied to Vx and V minus x respectively. So what does that mean? It simply means that the physical laws that we use, whether in classical physics or whether in quantum mechanics, they themselves do not distinguish a flipping of the signs of the coordinate axis. That means the universe that we live in is unable to distinguish right from the left. It is symmetric with respect to right and the left. This is what is called parity symmetry. This is a kind of a supposition that the universe is symmetric with respect to left and right. This is an idea which was held to be true for a long time before it was shown around 1960s that this idea was violated, especially when it comes to weak interactions. So you have 4 different kinds of interactions: the gravitational, electromagnetic, strong and weak interactions. Now for the first 3 interactions, we cannot find an experiment which will distinguish a left-handed system and a right-handed system. However, for weak interactions, it was shown by a scientist by the name of Chen-Xing Wu, who performed a particular experiment which involved beta decay of cobalt-60, and this experiment is very famously known as the Wu experiment, which demonstrated how this conservation of parity principle is violated, at least for the case of weak interactions. So before I talk about that experiment in detail, let's first do a revision of what is handedness or helicity of neutrinos, because that is a consequence of this particular experiment. Okay, so before I talk about the experiment which demonstrated violation of parity, let's first talk about a peculiar property of neutrinos. So neutrinos, as they turn out, are left-handed, and antineutrinos, the antiparticles of neutrinos, are right-handed. Now what do they mean? What does left-handed and right-handed particles mean? So in different books they speak of it in a slightly different way. So I am going to tell you the 3 different ways in which you can distinguish left-handed and right-handed particles. Okay, so left-handed and right-handed particles basically gives you an idea about the orientation of the spin with respect to the nature of its motion. Now before I show you the difference in these 2 particles, first keep in mind that the spin of a particle, especially quantum particles like neutrinos, are not the same as the spinning of objects like Earth or the planets. So when we talk about spin, physical objects, we imagine a ball which is rotating in space with respect to some axis, and because of this rotation they have an angular momentum associated with them. Just like Earth is spinning on its own axis, it has an angular momentum associated with it. However, quantum particles like electrons, neutrinos, they are point mass particles, so it would be wrong to think of or to say that they are actually spinning, but they do have an intrinsic angular momentum associated with it, which for various reasons is known as the spin angular momentum. So it is an intrinsic property of these quantum particles, and sometimes for the sake of discussion, for the sake of a better visualization, we say that the particle is spinning on its own axis, which is contributing towards this particular angular momentum. But just to be clear, there is no actual spinning, but it is helpful only for the sake of visualization and understanding of what we mean when we say there is a spin angular momentum associated with this particle. So having said that, there are three different ways of distinguishing like left-handed particles with right-handed particles. So the first way is by looking at the spin. Okay, by spin I mean the spin angular momentum. So for that I have a construction here which simply gives you an idea about the relationship of its spin and direction of motion. So this arrow represents the direction in which the particle is moving, and this plane represents, it is going to give us an idea about whether the rotation or whether the spinning is in the clockwise direction or whether the spinning is in the anti-clockwise direction. So left-handed particles like neutrinos, when they travel in a particular direction, they experience rotation in the anti-clockwise direction. Now before that I have drawn these particles with arrows here. Okay, so this is a neutrino, this is an anti-neutrino, and I have drawn this small arrow, the green colored arrow in both cases. I have drawn this big arrow in both cases. The small arrow basically represents the direction of momentum or the direction in which the particle is moving, and the bigger arrow represents the direction of its spin, which is associated with its angular momentum. All right, so if I look at the neutrino which is going in a particular direction, let's suppose away from me. So if, let's suppose, from your perspective the neutrino is penetrating this board, then the neutrino's spin would be in the anti-clockwise direction. This is what it means for a particle to be left-handed. On the other hand, if you look at the anti-neutrino as it is going away from me, so as it is traveling from your perspective, it is moving away from you, it is penetrating the board, then the direction of its spin is in the clockwise direction. That is what it means to be a right-handed particle. So that is one way of distinguishing left-handed and right-handed particles. There is another way. So if you use your right hand to curl up your palm in this particular manner, then if the curling of the palm represents the spinning, then the thumb represents the direction of motion. This is known as a right-handed particle. If I use my right hand to curl up my thumb, to curl up my palm in such a manner that the curling of the palm represents the direction of spinning and the thumb represents the direction of motion, and that's a right-handed particle. But for the case of a neutrino, I'll have to use my left hand. Where I'll use my left hand, I'll curl up my palm in such a manner that my thumb represents the direction of motion, and this is called a left-handed particle. So if you have to use your right hand to describe the relationship between the spin and the direction of motion of the particle, that's a right-handed particle. If you have to use a left hand to represent the direction of motion of the particle and its spin, then that's a left-handed particle. There is another way of distinguishing the right-handedness from left-handedness is by using these arrows. Okay, so as I said, the green arrow represents the direction of motion of the particle, the bigger arrow represents the direction of the spin angular momentum. So for example, if I use my right hand, all right, to curl up the direction of the spin, then my thumb points towards the direction of the spin angular momentum. All right, again, if I use my right hand to curl up in the direction of the spin, then the thumb represents the direction of the spin angular momentum. So this is the direction of the spin angular momentum, but if the spin angular momentum aligns with the direction of motion, that's a right-handed particle. If the spin angular momentum is opposite to the direction of motion, that's a left-handed particle. For that, I have created these arrows. All right, so this smaller arrow represents the direction of motion. The particle is moving in this direction. This bigger arrow represents the direction of spin, or the direction associated with the spin angular momentum. So if both these two arrows are pointing in the same direction, so if the particle is moving in the same direction as its spin, this is called a right-handed particle. If both of them are in opposite directions, so if the particle is moving away, from the opposite to the direction of a spin, that is called a left-handed particle. So I'll use both these two arrows to help us distinguish both these two particles. All right, so these are three different ways of distinguishing left-handed particles from right-handed particles. You can use any one of them, but for the sake of my discussion right now, I'll use these two arrows if both of them, the direction of motion and the direction of the spin associated with the angular momentum are in the same direction, it's a right-handed particle. If the direction of motion and the spin direction are in opposite direction, that's a left-handed particle. Now the peculiar property of neutrinos is that all the neutrinos that has yet been discovered experimentally in nature, they all turn out to be left-handed, while all the antineutrinos turn out to be right-handed. Now this seems to be a very peculiar property because other particles are not like that. You can have electrons which are left-handed, which are right-handed. You can have light photons which are left circularly polarized or right circularly polarized. But for the case of neutrinos, they are always left-handed, and for the case of antineutrinos, they are always right-handed. You will never find a right-handed neutrino. You will never find a left-handed antineutrino, at least not yet. And this is something that violates the idea of parasymmetry, or that is a result of the violation of parity conservation. To understand, let's look at its mirror image. So here I have placed the neutrino and the antineutrino in front of a giant mirror, and I'm trying to see whether or not this idea of the helicity of a neutrino antineutrino is reflected equally in the mirror. So by helicity, I said that the right-handedness and the left-handedness can be defined by a property called helicity. So for example, if a particle is right-handed, that means the spin and the momentum are in the same direction. It is said to have a helicity of +1, and if it is a left-handed particle, that means the spin and the direction of motion are opposite, then it's said to have a helicity of -1. Now what happens if I put a neutrino and an antineutrino in front of a mirror? Now in my previous video, one of you asked a very simple question, a good question, that how is it possible that these particles, which are so difficult to even detect, which is impossible to see, you can place them in front of a mirror. So the thing is, I am not literally placing a mirror in front of them. Why I put a mirror is just to give you an idea of what happens when we are doing a parity transformation. So I talked about parity when we inverted the coordinate axes, right? So the mirror is just to give you a visualization, just to help you in understanding what is happening. It has nothing to do with actually placing the neutrinos in front of a mirror. It is just associated with a parity transformation. And in some cases, I can look at the mirror image of a physical phenomena to get an idea of what the parity transformation does. Because in this case, if I assume that this particle is moving, let's suppose in the positive z-axis, then I can say that its mirror image will also be in the negative z-axis, right? So the mirror image is basically the z-axis inverted. So if I invert the z-axis, this will represent the mirror image. So just wanted to clear that point, that it's not an actual mirror I place in front of the neutrinos. It's just that we can understand the properties by imagining or visualizing a mirror which simply is associated with a parity transformation from a positive z to minus z axis. All right. Now, having said that, what is going to happen to the nature of its direction of motion and the nature of its spin? Now, I told you that linear momenta under a parity transformation flips. So I said just in the first half of my video that the linear momenta P under a parity transformation becomes minus P, right? That means if a particle is moving in this direction, under a parity transformation, it will be in the opposite direction. If a particle is moving in this direction, in the mirror, it will be in the opposite direction, right? But then I also showed that the angular momenta, and for quantum particles, the spin angular momentum, let's suppose capital S, under a similar parity transformation does not get inverted. All right, so the angular momenta which is associated with the quantum particles, they under a parity transformation do not change in its direction. So if I take this particular arrow, this direction remains the same in the mirror image. If I take this particular arrow, this direction remains the same in the mirror image. So the parity transformation is such that when you invert the coordinate axis, then it just so happens that the direction of the spin or the curling of my hand is going to remain the same, which effectively simply means that the direction of the spin, if I represent it by an arrow, will remain unchanged under a parity transformation in this particular case. Now, what does that mean for the case of a neutrino? So in the case of a neutrino, the spin and its direction of motion were inverted, right? But in the mirror image, they are in the same direction. That means in the mirror image for a neutrino, it's a right-handed particle. For the case of an antineutrino, the direction of spin and motion are in the same direction, so it's a right-handed particle. But in the mirror image, the spin and the direction of its motion are opposite. That means now it's a left-handed. So that means in the real world, neutrinos are left-handed while antineutrinos are right-handed. But if I perform a parity transformation, if I look at the mirror universe, then neutrinos turn out to be right-handed and antineutrinos turn out to be left-handed. Now that is not a problem for other quantum particles like electrons and photons, because electrons and photons are both left-handed and right-handed particles exist in our universe. But that is a problem for the case of neutrinos, because we have never seen a right-handed neutrino. We have never seen a left-handed neutrino. The weak interactions that lead to the production of neutrinos and antineutrinos have never emitted or interacted with neutrinos that are right-handed or antineutrinos that are left-handed. So up till now, all the experiments that have been performed do not demonstrate the existence of a right-handed neutrino. That means these particles with this particular property do not exist in our universe. So these do not exist in our universe. The only neutrinos and antineutrinos that do exist are them. So it just so turns out this very peculiar fundamental property of neutrinos is that all neutrinos out there are left-handed and all antineutrinos out there are right-handed. Now if the universe was parity-symmetric, then both left-handed and right-handed neutrinos should exist. Both right-handed and left-handed antineutrinos should exist. But that is not the case. Right-handed neutrinos and left-handed antineutrinos do not exist, which is fundamentally a result of the violation of parity symmetry of this universe, and that can be demonstrated by the beta decay processes, which was used to experimentally show how the weak interaction violates parity. And that was one of the first experiments which was performed by Chen-Xing Wu in 1956 that showed how parity symmetry is violated, at least for the case of weak interaction. So let's talk about that experiment. Okay, the experiment that was performed involved a very common decay process, which is the beta decay process. All right, here we have the beta decay of cobalt-60. So the experiment that was performed by Chen-Xing and her team looked at basically the beta decay of cobalt-60. The cobalt-60 is a radioactive nuclei which experiences beta decay to become nickel and leads to the emission of an electron and an electron antineutrino in the process. Beta decays are essentially the result of weak interaction, because if you look at the decay of this nucleus, the cobalt-60 nucleus to a nickel-60 nucleus, then it simply involves the transformation of a neutron inside the cobalt-60 to a proton, which is now inside the nickel-60, right? And this leads to the emission of an electron and an electron antineutrino. Now, what is a neutron? Neutron simply is made up of quarks. It involves one up and two down quark, while the proton is made up of two up and one down quark. That means a down quark is transforming into an up quark, leading to the emission of an electron and an electron antineutrino. This is a very good example of the weak interaction, because only the weak interaction is responsible for the transformation of quarks. So the quarks do not change identity due to gravitational or electromagnetic or strong interaction. The only way that quarks change identity from, let's suppose, up to down or down to up involves weak interaction. So this is a very good example of the consequences of a weak interaction. Now, if you look at this particular beta decay, which was the experiment performed by Wu and her team, then you come up with something very, very interesting, at least from the perspective of parity. So that has to do with the direction in which the electron is emitted with respect to the cobalt-60 nuclei. All right, so usually in the case of a normal crystal structure, the cobalts might be randomly oriented in space. So what they did was they placed the material containing cobalt-60 in the presence of a strong magnetic field. So the strong magnetic field, what they do is they align all the cobalt-60 spins in one particular direction. So if the cobalt-60 has a particular spin, all of the nuclei will be oriented in this particular direction. So if you look at the decay process itself, if you look at the nuclei and the spin involved with the nuclei, as it turns out, the cobalt-60 has a spin of 5. The resultant daughter nuclei nickel has a spin of 4. Now, what is spin? Spin, as I just now told you, it is associated with the angular momenta, which is an intrinsic property of different quantum particles. And in this case, the parent nuclei and a daughter nuclei have a spin of 5 and 4 respectively. Now we know that electrons are fermions, so they can have spin of plus half and minus half, and even neutrinos are fermions, so they can have a spin of plus half and minus half. To balance spin angular momentum in this particular case, the electron must carry out a plus half spin and the neutrino must carry out a plus half spin. Okay, so conservation of spin angular momenta is a very important conservation law that particles follow. So to maintain conservation of angular momenta, if the cobalt and nickel has 5 and 4 spin respectively, the electron must have plus half and the neutrino must have plus half. Now what does plus half and minus half really mean? Just to give you a small brief recap, with respect to some arbitrary z-axis, which in this particular case represents the direction of the magnetic field, the electrons and neutrinos, which are fermions, they can orient themselves in two different directions. So the electrons can have an angular momenta of plus h cross by 2 or minus h cross by 2 in the positive z-axis or in the negative z-axis. Okay, so I've talked about spin angular momenta in one of my previous videos. What simply means is that these quantum particles, they can have an angular momenta with respect to an fixed z-axis, either in the positive direction or in the negative direction, and their magnitude in the z-axis can be either plus h cross by 2 or minus h cross by 2. That's what it means. Plus half electron simply means that the z-axis component of the angular momenta is plus h cross by 2, and minus half means that the z component angular moment of the electron is minus h cross by 2 in the negative z axis. So in this case, the conservation of angular momenta simply tells us that the electron must be plus half and the neutrino must also be plus half. Now how does that manifest itself in this kind of experiment? As it just so happens is that the cobalt-60 decays into nickel and the electrons and neutrinos are emitted. Now the electrons and neutrinos can be emitted in either direction. It can be emitted in forward and backward direction. So let's look at two different scenarios. Now I just told you that a magnetic field is provided so that all the cobalt-60 nuclei can orient themselves such that their spin are all directed in the direction of magnetic field. So that means for every cobalt nuclei that are in rest, okay, they are not in motion, that are in rest, their spin arrows will be pointing towards the direction of the magnetic field. That means the spin is in the positive z-axis. So this is the positive z-axis. Okay, now since because of conservation of angular momentum, both cobalt and nickel after the emission are at rest and their angular momenta are 5, 4 and plus half respectively, that means the direction of the spin must be the same. That means it must be in the positive z-axis. Okay, the direction of the spin must be in the positive z-axis. If the particles had minus half, then it could be in the negative z-axis, but in this case it must be in the positive z-axis. Now what does that mean for our case? So we can have two distinct scenarios possible. Let's understand the scenario, then you will understand and appreciate what the experimental result revealed. So the cobalt-60 has spin in the positive z-axis. Alright, the cobalt-60 has spin in the positive z-axis. Now I said that the electron and the neutrino, antineutrino must also have spin in this particular direction. So whatever particles are emitted must have spin in this particular direction, not in the opposite way, in this particular direction. Now apart from conservation of angular momenta, there is also conservation of linear momenta. That means if electrons are antineutrinos are emitted, they must be emitted in opposite direction. That means the linear momentum must be in this direction. So if the antineutrino is in the forward direction, the electron must be in the backward direction. In the second case scenario, if the electron is in the forward direction, the antineutrino must be in the backward direction. Yes, so you're understanding what is happening. Both the particles are emitted in the forward and the backward direction with the spin pointing in the same direction. Both the particles are emitted in the forward and in the backward direction with the spin pointing in the forward plus z axis. Now both of these scenarios are possible as far as conservation of angular momentum and conservation of linear momentum is concerned. There is no physical law that prevents any one of these scenarios from happening, except for the fact that I just now told you that neutrinos are always left-handed and antineutrinos are always right-handed. So if you look at, let's suppose if you look at the electron in both these two scenarios, the electron and linear momentum and spin angular momentum are in the opposite direction. That means it's a left-handed electron. While in second case scenario, the spin and the direction of motion are in the same, so that it's a right-handed electron. But for the case of our antineutrino here, In the case of this antineutrino, spin and the direction of motion are the same, so it's a right-handed. But in this case, the spin and the direction of motion are opposite, so this is left-handed. So in one scenarios, left-handed electrons and right-handed antineutrinos are emitted. In the other scenario, left-handed antineutrinos and right-handed electrons are emitted. I just now told you that left-handed antineutrinos are not found in nature. No weak interaction whatsoever actually leads to the emission of a left-handed antineutrino. So even though both these two scenarios are energetically possible, they are possible through conservation of linear momentum, they are possible through conservation of angular momentum. In fact, they don't violate any other known laws of physics, but both these two scenarios don't seem to happen. Because if they did, it would lead to the creation of left-handed antineutrinos which are not seen in nature. Now, if you compare this kind of a decay process, let's suppose, with some other decay process which involves let's suppose like a photon, because in this case the nickel is excited, the daughter nuclei is excited in its state, so it also ends up leading to the emission of photons. Now if this nickel daughter nuclei ends up emitting photons, these photons will have both left-handedness and right-handedness. The photons, if you look, they will be emitted in both directions with 50-50 probability of being left-handed or right-handed. A photon being left-handed means that it's simply left circularly polarized, and right-handed means it's right circularly polarized. Even in nature, left-handed electrons and right-handed electrons are found, right? So even though right-handed electrons are indeed found in nature, left-handed antineutrinos are not. And this is something which the experiment revealed itself by looking at the study of the decay of cobalt-60, that the team led by Wu found out that even though if parity was conserved in our universe, if our universe did not differentiate between a left-handed and a right-handed system, if our universe was symmetric with respect to left-handedness and right-handedness, then both these two scenarios are possible and they should happen. But the experiment, after it was performed, found out that only one of these scenarios happened, the other did not happen. This did not happen at all. Only the first scenario happened. That means the electrons which were emitted were always emitted opposite to the spin direction of cobalt-60, never in the direction of the cobalt-60 spin. So even though both these scenarios are possible if parity is conserved, but that did not happen. The experiment revealed that only one of these scenarios indeed took place, that the electrons were always emitted opposite to the direction of the cobalt-60 spin and never in the direction of the cobalt-60 spin, which violated the conservation of parity. And we can see that by again drawing a mirror image. So if you look at the results of this experiment and the mirror image associated with it, in that case you can see that the cobalt-60 had a spin in a given, let's suppose, positive z-axis, right? The electron which is emitted also have a spin of +12 in the same positive z-axis, but the electrons were preferentially emitted in the direction opposite to the cobalt-60 spin, which is in the negative z-axis. Now how does it look in the case of the mirror image? So if you have the cobalt spin here, as I just now said just a few moments ago, that under a parity transformation the linear momenta direction gets changed, but the spin directions or the spin angular momenta directions do not change. So under a parity transformation, which can be visualized for the sake of convenience, for the sake of understanding, using this mirror image where this represents positive z-axis, this represents negative z-axis, the cobalt-60 has a spin in this particular direction, the electron is emitted in this particular direction with a spin in this particular direction. So in the real world, the electron is emitted opposite to the cobalt spin, but in the mirror inverted world, the electrons are emitted in the same direction as the cobalt spin. Are you getting it? In the real world, what the experiment performed by Wu demonstrated is that the electrons were preferentially emitted opposite to the direction of the cobalt spin, but its parity inverted case, the mirror images where the cobalt spin is directed in the or the electrons are emitted in the direction of the cobalt spin. Now what does conservation of parity tells us? It tells us is that this phenomena is equally likely as this particular phenomena. That is what conservation of parity is. That is what parity symmetry is. That the mirror image of a phenomena is equally possible in our universe. That means the universe cannot distinguish a left-handed and the right-handed systems. So if this is possible, then in a universe which conserves parity, this would also happen. But this never happened. The electrons were preferentially emitted opposite to the direction of the nuclear spin. They were never emitted in the direction of nuclear spin, which therefore violates this idea that conservation of parity is always true. So let me repeat that. The experiment showed that the electrons are preferentially directed opposite to the cobalt-60 spin, but its mirror image or parity-inverted phenomena means that electrons should also be emitted in the direction of the cobalt-60 spin, but this does not happen in real world. When these experiments are performed, this does not happen. Alright, if parity was conserved, both of these phenomena should have happened and should have been equally likely, but this does not happen. Only this happens. That means the electrons emitted are always in the direction opposite to the cobalt-60 spin, thereby violating this conservation of parity principle. That means somehow the laws in our universe can distinguish between what is left-handed and what is right-handed, because if you look at all other interactions, gravitational, strong and electromagnetic interactions, in none of the interactions can you distinguish what is left-handed from what is right-handed. There is no preferential treatment to the system evolving from one particular direction. But in the case of weak interaction, there is a particular preference towards a particular handedness, and this goes back to the transformation of quarks. So in this particular case, a down quark transformed into an up quark, leading to the emission of a lepton particle like electron and an electron antineutrino. Now, it just so happens that these quarks have a left hand side and a right hand side. They oscillate between both. The quarks oscillate between a left hand side and a right hand side. And when a quark is oscillating between a left and a right hand side, only one of these sides participates in the weak interaction, which is the beta decay process. So somehow our universe can distinguish between what is left and what is right. That means if I gave you this particular phenomena and if I gave you the mirror image of this particular phenomena, you can directly say that one is possible, the other is not possible. But under parity conservation, that is not true. Under parity conservation, whatever phenomena I give you and the mirror image I give you, both of them will be equally likely, and you will not be able to distinguish which one of them is allowed and which one of them is not. But only for the case of weak interactions, it just so happens that the phenomena that happen and their mirror images that do not happen can be easily distinguished, and thereby this kind of experiment ended up demonstrating the violation of the parity symmetry in our universe. So that is all for today. That's it. Thank you very much.